very much. I'd like to start by thanking the organizers for organizing this amazing conference. It's a pleasure to be here, and there's so much to learn. I'd also like to start by, thanking Anna Karyani and Mingzhe Zhang for giving this amazing lecture series. And so I'm in a very fortunate position where I don't have to really motivate and introduce the kind of objects I want to study. So I think we can jump right into the main theorem and sort of the outline of the proof of what I want to talk about. So here's a setting. So Gx is some arbitrary Shimura datum. It has reflex field E. I choose a place E over P, and then I look at the corresponding local field, and G is the local reductive group. And then it induces a Hodge co-character defined over QP bar, and it's really a conjugacy class of Hodge co-characters, but I'm going to fix one. And then the only difference is that I'm going to look at the Shimura variety at infinite level, both at P and away from P. So it's going to be some larger tower, but I think it's useful because it's easier to formulate the away from P action if I do this. So let me do that. And in the first talk, Mingzhe Zhang introduces this Hodge-Tate period map from Shimura variety of K, sorry, not K, of Gx to the flag variety for mu inverse. And let me also put an E to indicate that it's actually a variety defined over E. And she used some kind of the universal abelian variety and looked at its Hodge-Tate sequence and so on. But it turns out that this map exists for all G, even if you don't have kind of a motive associated to the Shimura variety. So this always exists by work of Liu Zhu. And it's also explained in David Hansen's Wolflog report that how to construct this kind of a period map. OK, so I don't have to really assume anything about G and X. It can even be something exceptional. It doesn't have to be satisfy this condition that the Q rank of the connected center is the same as the R rank of the connected center, and so on. So it really works for arbitrary Gx. Okay.
So does it use information on integral models?
No, it does not use integral models at all. So this is a very general fact about the fact that there is a DRAM local system over the Shimura variety, and then it's a purely p-adic Hodge theory fact that you can use. So it comes from DRAM local systems. And DRAM, sorry, over Shimura varieties.
And this is the non-compactified.
This is non-compactified.
Okay.
Yeah.
But in that generality, I guess one doesn't know that the Shimura variety is perfectoid.
Right. So the Shimura variety is we don't know that it's perfectoid, but I'm just taking. Right, I'm first taking the associated V sheaf and then taking the inverse limit as V sheaf. So it's still some V sheaf, but I don't really care about its perfectoid, for the purpose of this talk. Yeah. OK. So, right, so I do have this map always. And another thing I have to mention before I can state the definition is for every V sheaf, V sheaf or V stack X, there exists a canonical Frobenius from X to X, which is just given by induced from the Frobenius on the category of perfectoids itself. So every perfectoid space has a Frobenius, absolute Frobenius, and it sort of, well, just directly induces a canonical Frobenius on every V stack. Even something like split QP has a Frobenius. And it's also automatically functorial with respect to x to y, map of V sheaves. And then I want to also note that, so there is a canonical isomorphism from the identity map on Bun G to the Frobenius of Bun G, which is admittedly a little bit confusing, but the idea is that the Frobenius acts as the identity on the Farks-Montagny curve. I think we've been using this notation, Farks-Montagny X. So this kind of induces a natural isomorphism between the identity and the Frobenius on Bun G. And what it really does is, if I think of Bun G as a kind of a p-divisible group up to quasi-isogeny, this is sort of a Frobenius pullback, and this really records the relative Frobenius. Of a p-divisible group. But if you sort of change it into the perspective of a vector bundle on the Farks-Montagny curve, the Frobenius kind of gets, the Frobenius descent atom becomes like unraveled, and this is just coming from the fact that phi equals identity. Okay. So now let me make an axiomatic definition of the Igusa stack using that. So here's a definition. Let U inside the Shimura variety be a V sheaf, be an open V sheaf, stable under the actions. Maybe I put an underline here. So now an Igusa stack is a data of I first want a V stack x U of Gx, a V stack with a prime to P K action. So I want a map from this thing to Bun G. So it's a G A P this thing. Let me say equivariant map from xu of Gx to Bun G, called we call it pi Hodge-Tate bar. And so Bun G is a stack, so this really is right. And by the way, I should say this is the action is trivial action. And this really contains some kind of equivariance coherence datum as well, but I'm going to kind of ignore that. And third, I want that a two Cartesian diagram. That's sort of familiar to us. U maps to xu Gx. This should map to, by the Hodge-Tate period map, to the flag variety. This would map to, via the Bobby-Laszlo map, to Bun G. And I'll put a, this is also bounded by mu inverse, so I should put a mu inverse here and mu inverse here. So this was a pi Hodge-Tate bar. And well, I think this is sometimes called Qx. And then I need some properties such that so the first thing is that I want this sort of isomorphism to be Hecke-covariant. So the isomorphism U to sort of the Igs Gx times Bungie flag variety is G a infinity covariant sorry? Mu. This mu. So this is the Hodge-Tate character over there. So this, yeah, it's the same thing. And then there's the last condition, which is that, well, so roughly speaking, I want the Frobenius on the Igusa stack to be trivial. But again, this Igusa stack could be a stack, so then it's a little bit hard to describe it that way. So, so to be technically correct, I need to say, so the phi times identity action on this thing is trivial. And then to define the phi times identity action using phi on Bungie is identity on Bungie. So, and that is the end of the definition. And I admit it's a little bit of a mouthful, but it's really just this Cartesian diagram plus Hecke, sort of the natural Hecke covariance we want, plus this tiny fact that the Frobenius acts trivially on the Igusa.
Is a Hecke covariance, is it that's the same as saying that the Q is Hecke covariance and then the pi is Hecke covariant?
Sorry. Q is Hecke covariant, and then this is Hecke covariant. So I think it's, so I think one needs to be a little bit careful because that's a stack, and it's, I think, a little bit annoying to just say that. I mean, it's a little bit, yeah, I think there's some stackiness issues that come into play.
So being equivariant is a datum because of the stack.
Right, so the second, right, second condition, second thing is still a data. It's a map plus some Hecke, well, some coherence datum.
And the condition of being equivariant, that the equivalence is equivariant, is again
it's a condition now. And so there's one data and then one condition because it's like one truncated. You don't have to, it's no infinite, it doesn't go forever, it just stops. Yeah, U is a sheaf, so right. So these things are both sheaves. So here it's everything's makes sense. Yeah, here it's fine. Here this is a sheaf, that's also a sheaf. Everything's fine. Yeah. So it's yeah. So I'd like it to be a little bit simpler, but not very good at sort of higher categorical languages. So it's, I think, one concrete way of saying everything I want to say. Okay. So right. So the main theorem I want to prove or explain is that there are three parts. So the first part is that this Igs, so if this Igusa stack exists, it is unique up to unique isomorphism the second part is that if I have a morphism of Shimura data prime to x prime, then it uniquely induces corresponding map on Igusa stacks. And then, sorry, I have a U, so I guess I also need to put in that condition. So that if this maps to that, and under the natural map between Shimura varieties, if U maps to U prime, then this would map to that. Of course, assuming that these things exist. And the third part is a kind of a sort of the fact that you can pass to sub-varieties. So if gx mapping to gx, g prime x prime is a closed embedding, is an embedding, meaning that it's an embedding on g's, and u prime of g prime x prime exists, then for u being the intersection, this also exists. So one thing I want to say is that I've never used sort of integral structures. So this is something that still makes sense for exceptional Shimura varieties. And this kind of a functoriality or uniqueness, it also doesn't use any rational. It doesn't use any integral structure. It only uses a rational one. OK, so why is this kind of a statement useful? Maybe I'll quickly say some uses. So the one thing is part 3 is something about existence for a closed subvariety. So Mingzhi Zhang tells us that basically Siegel Igusa stacks exist. And an immediate consequence of this is that there exists for all Hodge type Gx. There exists Igusa stacks for both the good reduction locus and the entire thing. And this is a thing that will sort of base change to the good reduction Shimura variety. And this is a thing that will base change the good reduction plus bad reduction locus of the Shimura variety. Yeah. So that's one thing that can deduce. Another thing is functoriality.
Can I ask something?
Yeah.
Do you also get the exceptional case that are not covered by Michael's?
So, for existence, no. It seems, yeah. I think the exceptional case is widely open.
Wait, so Zhang only constructed the good reduction locus, but then
Right. So but then she also constructs. So the way this goes is she also constructs it for minimally compactified things for GSP at least 4, and then you can kind of remove the boundary, so you get these things for GSP at least 4, and then every Hodge type embeds into GSP at least 4. Including GSP, GL2.
So if you just remove the boundary from her construction, like a pactified thing,
yeah.
Does that gives you already a candidate, or that's not a Igusa system?
That gives a candidate.
Okay, and then you show it's actually the unique one by this.
Yes, uniqueness is, yeah, it's always, so you don't have to worry about like 2 different things being compatible. Right. So the second thing I want to mention is functoriality sort of gives us sort of extra symmetries. Of the Igusa stack. And one of the examples is sort of if I have an element of G add of Q such that, well, I guess, well, maybe I should say in the image of GR to G add of R, then there's a conjugation action by X, which actually defines a map from X comma X, sorry, G comma X to G comma X, and that gives a conjugation action on Igusa stacks as well. And this is sort of the main thing that goes into this work in progress of constructing Igusa stacks for abelian type Shimura varieties. You kind of exploit this kind of symmetry to be able to construct abelian type Igusa stacks. Right, so another thing I can mention is uniqueness also holds for compactified Igusa stacks. And let me not say too much about it, but it's kind of, if you look at the argument and try to adapt it to compactified Igusa stacks, it also holds. So that's something you can check. And maybe the fourth thing is, by uniqueness, well, you can construct kind of a, you can construct like some parts of the Igusa stack sort of ad hoc, in an ad hoc way, and then we kind of know from this theorem that it's going to agree with the other constructions of Igusa stack. So you can imagine, so this is kind of maybe a hypothetical one, but imagine gluing different Igusa stacks along their intersections. So, so the thing I'm imagining is maybe you can try to construct compactified Igusa stacks by first knowing that they exist on the entire Shimura variety, and then somehow analyzing their tubular neighborhoods of the boundary, and then showing that these extend. So maybe potential applications, potentially useful for compactification. And then maybe I'll just write a question mark, because it's not really concrete at this point. OK, so I think I have roughly 30 minutes, and I'd like to try and explain how this how the proof works. And it's actually going to be a really, well, I think it's a really fun proof. So I hope to explain some of the geometric ingredients that go into that, unless there are questions. So the first step, or the 0th step, is to interpret this as a kind of a uniformization. Well, interpret the Igusa stack as a kind of a uniformization of a Shimura variety. So, right, so what I mean by that, so this Igusa stack, whatever it is, it's going to be surjected upon by, let me ignore all the u's, it's surjected upon by the Shimura variety. And then it's going to be basically a quotient of the Shimura variety by some relation. And if I believe in this Cartesian diagram, this will be the Shimura variety times 1G with the flag variety. So, well, then we call this projection 1, and call this projection 2. And if I look at this composition, this is still going to be projection 1. So there's nothing really happening over here. But now this map is kind of interesting. And the point is that once I have this map theta, I can actually be able to write down the Igusa stack as the quotient of the Shimura variety by whatever this is along the projection map and theta. So, Igusa stack basically corresponds to a theta from this relation G mu inverse E, which I'm going to call just R for relations. So to the Shimura variety.
But there is also a composition law for R on this relation, which is important for the stack. In case the stack is out of shift, it's important for the.
Right. So it turns out that if I take this kind of, if I look at a map theta from here to here, the composition law is actually also can be expressed in terms of theta. So I mean, if I take this times flag, that's going to be the fiber product of this over that. And now I can define 3 different ways from here to go to flag variety, given by, well, I can, how does it work? So I can say projection to the 1, 2. I can have a theta times identity, and I can have a theta, projection 1, 3. So I think these are the 3 things I can use to. So everything actually is encoded in theta. I think I should. And moreover, so theta satisfies some very basic properties such that theta is equivariant with respect to some kind of I have a GA infinity action times G QP, and I can sort of, right, if I write it as A upper P, comma A lower P, comma B lower P maps to A upper P, comma BP lower P. This is lands inside GA infinity as well, and it's covariant with respect to this. There are some other conditions such that, like if I look at Shimura variety times flag variety, if I start with the Shimura variety, if I look at the graph of the Hodge-Tate period map to Shimura variety times flag variety, then map it to theta. That's going to be the identity map on the Shimura variety. And then this also has a map to the flag variety. And that has to be a sort of a second projection map, and so on. I'm not going to list all the things, but it's but essentially the Igusa stack becomes map theta together with some satisfying some formal properties, and then we really do get an equivalence between an Igusa stack and map theta. And so uniqueness.
Why do you call this uniformization?
So I'll try to explain this in like 5 minutes. So uniqueness, well, is equivalent to uniqueness of theta. Functoriality is equivalent to the some diagram commuting this commutes, where this is theta and this is theta prime, and what else is there? Closed embeddings, passage to close embeddings is equivalent to well, theta of some closed Shimura variety, theta prime of some closed Shimura variety times flag of G is contained inside Shimura variety of G. And theta prime is something bigger than that. So I can translate all these properties of theta, well, this entire theorem into some statements about theta, and then I can just try to analyze what kind of properties theta has to satisfy. Okay, right, and why do I call this a uniformization? So, okay, so in Mingja's lecture, she only worked at the good reduction locus, but let's do that as well. So roughly what is happening, so roughly what is theta doing? So if I have theta from, I can even use the modular curve, but let me just write it here and then assume it's a modular. It's a case of a modular curve, bun G, flag variety to right. So a R plus point here is kind of a, well, here I have I'm fixing a untilt R sharp 1 plus together with a elliptic curve E over R sharp 1 plus. So that's what roughly the point of a Shimura variety would look like. And the flag variety, if I pass to sort of finite level, what it's doing is it's essentially fixing a p-divisible group. So it's an untilt R sharp 2 plus together with a p-divisible group x over R sharp 2 plus. And then I have a fiber product over bun G, and this is extra data because bun G is a stack. And what it's specifying is it's a quasi-isogeny alpha between E p infinity, for base change to R sharp 1 plus mod pi sharp 1 to x tensored over R sharp 2 plus with R sharp 2 plus mod pi 2 sharp 2, sorry, pi sharp 2. And it turns out that even if I have two different untilts, I can choose this uniformizers pi and pi sharp 1 and pi sharp 2 such that r sharp 1 plus mod pi sharp 1 is isomorphic to r sharp 2 plus mod pi sharp 2. So this is really happening over the same ring, and then I have a quasi-isogeny over there. And now what I'm doing is I'm taking my elliptic curve, I'm reducing mod pi sharp 1, I'm modifying it along this quasi-isogeny, and then this is some elliptic curve with p-divisible exactly that, and then I'm Stanford lifting it to some elliptic curve with this p-divisible group, and that's how I get theta. And then I get something here, and it's a uniformization in the sense that if I take a point here and just look at this fiber, I'm sort of mapping a Rapport-Zing space into the Shimura variety. So it's doing this uniformization in like a global family over the entire Shimura variety. Okay. So I feel like I haven't said anything with too much content so far. So I'd like to do that.
It's defining the generality where you don't have p-divisible, I mean.
Right.
Okay.
Yes, so that's sort of the entire point is to do this when I can't interpret it can't interpret these flag varieties or some integral models of these flag variety modulo some compact group as a moduli of p-divisible groups. Right.
Sorry, but in Rapport-Zing uniformization, is it also like a product of Shimura right and this Rapport flag variety?
Well, maybe there are more general versions, but my understanding was usually you fix a starting point, and then you look at the Rapport-Zing space mapping into the Shimura variety given by that kind of a modification starting at a fixed point. That's maybe it's more general, but right. So step 1 is to look at to understand, and by understand I mean prove uniqueness of the map theta over E. So what is that? Which is just my notation for theta restricted to RE, RE, where RE is well, I take the Shimura variety, and I take the product over 1G with the flag variety. But I don't deal with this fact that I might have different untilts. So I also fix an untilt over E. So that is going to be, well, essentially what this is sort of maps to, let me do it this way. So split E maps to split E times split of KE, split E, which sits inside split E times split E. And this is essentially the base change of my R. And let me also put an intermediate thing, R, RKE, just to for future use. So this is so my theta map is supposed to map R to the Shimura variety, but I'm going to restrict to the case when I don't have to deal with different tilts. And then step 2 is to understand theta and somehow bootstrap the uniqueness over here to a uniqueness over R.
So what's the final product? SPD cross SPD over what?
SPD over E, the local reflex field.
Yeah, E is the local okay, this is the diamond, but what is in the right?
Oh, here. This is KE, the residue field. Of E. So this is kind of like a connected component inside E times E. Yeah. Okay.
So at this point, you're assuming you have a map theta and you want to say things about it. Is that right?
Right. I want to prove that it's unique and functorial. Okay, so how do I deal with this this map? So fix. Well, so step 1. Well, I'm going to fix some compact open small enough G A of infinity and then because I have a Hecke covariance, I can actually just pass to level K. And here I'm technically assuming this SV5 condition that makes these things have a KP local system and so on. To this flag variety G mu inverse mod KP to Shimura variety. And now this is sort of the moduli of the Strikas at KP level. So in particular, sorry, I'm also taking a bungee over E here. And in particular, every fiber, like a fiber, if I look at the projection map to the Shimura variety, every fiber of projection 1 is actually a local Shimura variety. In the sense of, well, Schulze-Weinstein. So this is some nice kind of space that lives over the Shimura variety. And one thing I can remark is it turns out that this total space, we call this REK. REK is representable by a smooth rigid analytic variety. Which I don't think I need to use, but it's a kind of a curious fact, because if I try to do this sort of integrally, it's going to be some horrible in scheme that's not a formal scheme. So it's a kind of a curious thing that happens. Right. Right. So now I want to prove that this map is sort of uniquely determined. And so if I think about this as a moduli space of Shtukas, well, I know that if I make a trivial modification, or if I just look at the graph of the pi Hodge-Tate, it has to map to itself. So, well, essentially the idea is for every point here on a small open neighborhood, I'm going to say that, well, for every small open neighborhood of the image of pi Hodge-Tate inside here, which is still a rigid analytic variety, it sort of has a unique way to map to the Shimura variety. So how do I say this nicely? So we consider the map from the Shimura variety to this flag variety mod kp and to Bun-G. So again, so heuristically, this is taking a point in the Shimura variety and then associating its corresponding p-divisible group up to isogeny. And let me call this composition tau. And now the theorem I want to use is that whenever we have a tau coming from a de Rham local system, there is some kind of a rigidity associated to tau. So for every rational point.
You said for every and you wrote exists. Which you said for every and then you wrote exists.
This one?
Yeah.
Well, this is the next part of the statement of the theorem. So there exists, well, okay, maybe I'll, sorry. Whenever you have, okay, sorry. So for every, yes, I understand what you're saying. For every rational, okay, let me put a name for here. So y over f to Bun-G, for every rational point, y inside y of f, there exists a small open neighborhood, an open neighborhood such that U mapping to inside Y mapping to Bun-G and U sort of living over with F. This is a structure map mapping to tau Y to Bun-G are uniquely isomorphic. And then extending identity at Y. So what does that mean? It means that if I have a, so sort of if I imagine a formal scheme and a p-divisible group over that, at each residue disk, I'm going to have the same p-divisible group, the same isogeny class of a p-divisible group. And then I'm claiming that this can be actually done sort of rigid analytically. So so F is my, F is a finite extension of QP. And I think it's probably fine to have any finite extension of W of a perfect field, I think. Right. So Okay, so the intuition comes from really p-divisible groups over a formal scheme, but it uses this wonderful theorem of Shimizu that says, well, let me just say that, well, I say this, for every, well, there exists a U such that the DRAM local system restricted to U is a horizontal DRAM. So it's some serious p-adic Hodge theory fact, sorry, horizontal semi-stable after field extension. But let me, I don't think I have time to say more about this. Sorry. So given this, why is that a useful thing? How do I actually know that there is a unique theta? Well, so what I do is I look at that, so fix a f point y inside the Shimura variety times Shimura variety at level k times bun-g times z to the flag variety mod kp. Sorry, don't have to do this part yet. Shimura variety, and then I'm looking at the f points here. And then if I restrict to this fiber, I'm going to get a map from theta k comma y e from some local Shimura variety that I'm going to call g tau mu at level kp base change to f. So this is the fiber of the second projection map. Sorry, the first projection map written over there. Mapping to the Shimura variety at level k. Okay. Now, using this theorem, there exists a neighborhood W ky inside Shimura variety k x base change to f such that tau is trivialized and once tau is trivialized, I actually have a map in the other direction because I already have a Stücke on the Shimura variety. Now tau being trivialized gives me a framing of the Stücke, and then I get a map from W ky inside the Shimura variety base change to f to the local Shimura variety g tau y mu kp f, because this is essentially the moduli space of frame Stückes. And then, if I look at the map from theta, theta, I guess, ky e inverse of wky, this is also a, well, how do I say this? Right, so this is all, we have this map, which gives me a framing on here, and that's also has to be the identity map because there's a sort of a unique framing. So the tau is uniquely isomorphic, and there is always already an identity map down here, or the inclusion map, I should say. And there can be only one map, so this actually has to be the identity map. So This is the identity map, but the dimensions are the same, are equal, and therefore we see that theta just has to be the inverse of original map. Well, let me call this FR of FR of this frame, the map that the framing induces. So, in short, theta is sort of uniquely determined on a small open neighborhood of Y, and by analytic continuation, theta is determined on the connected component of Y's, I guess Y0 inside the base point of this local Shimura variety. Right. So, but this is on one connected component, and at this point we have to use some kind of a Heck covariance. So another theorem, which was observed in Gleason, Lim, Xu, and which is based on a result of Gleason, it was Lorenzo. Sorry. Yep. Which says that G of QP acts transitively on the limit as Kp goes to 1 of pi 0 of the local Shimura variety. And once we have that, now we can use this kind of a Heck action to actually say that this is completely determined at all level, and then we can pass the limit. That tells us that we can also collect it for all y, and that tells us that theta upper E is uniquely determined. So that's the rough sketch of how this is proved. And I also wanted to say something about theta, about the second step, but I think I'll have to stop here.
Maybe. So do you actually expect that your user step is a sheaf, given that you trivialize the action?
I think it's kind of, I think it should be, well, I do expect it to be true, but I don't. You expect that? I think I expect it to be true, but I don't think I prove that.
But because in the Ziegler case it is true, right?
Yeah, I think it's in Hodge-Tate it's okay.
Hodge-Tate it's in.
Do you expect the uniqueness to extend to the compactified Shimura time?
Yes, I think that was the third part I kind of, said. So, so the idea is, well, we just need theta to be unique, but the compactified thing is kind of, it's very, I mean, the open part is dense inside the compactification. So I think, just by.
Could you maybe explain how you show that this, what was RKE is representable by a smooth rigid space?
Right. So it's essentially the same proof you do when you're trying to show that local Shimura varieties are representable. So you map it to some kind of a relative flag variety over the Shimura variety, and that's even a scheme because it's associated to the automorphic vector bundles, and then whatever that is, that's going to be tal over that. So you. So you do have to, there is some input, you have to sort of unravel the definition of what this map from, what the Hodge-Tate period map is doing, and then there is some unraveling to do, but at the end I think it's essentially the same proof.
Okay, let's thank the speaker again.